And I'm still paying you. I got the hard ass beats like the crack of the tech. Still paying you. Think y'all forgot what rap sounded like? I'm still paying you. Back to match up beats, the bang of the average. Still paying you. I'ma make y'all pay for.
All right, round of applause for DJ Cash. Thank you. A lot to cover, and people have comments from feedback for you, so we'll get to that in a second. But this is the first time we started on time all semester, so yay, awesome, right? And it's also the most important lecture because it's going to be the most important data structure in all of computer science in all the world. It's going to be B+Trees, and so hopefully today I'll convey to you why that's the case. I don't care about any other data. I mean, we care about them because we need them, but it's all about the B+Tree. That's the most important thing. All right, so again, reminder, Project 1 is due this Sunday coming up. We had a recitation last week. The video is on Piazza. Go to that post there along with the slides. And then, as I said, beginning of the semester, for every project, since they're all due on Sundays, and we don't have office hours on Saturdays and Sundays normally, but the day before the project is due, we have a special Saturday office hour with multiple TAs for multiple hours on campus. So you can come and ask, hopefully, what aren't last-minute questions like how do I get started, like more deeper things to help you try to debug things. Okay? Then homework 3 will be released on Wednesday, and that'll be due on October 5th. And then just as to put this in your radar, the midterm exam will be in this room on Wednesday, October 8th. And it's going to cover lecture 1 to 11 inclusive, all that material up to and including, but not the week of the exam. So the week before the exam, all of that will be on there. And then I'll release a study guide with a practice exam next week. Okay? Any questions about any of these things? All right, so also starting today is we're kicking off the beginning of our seminar series this semester. So a bunch of you emailed and reached out and said, "How I love databases, maybe not as obsessively as much as I am, but like I do. But like, how can I get more databases in my life and go beyond the course?" So again, we have these optional seminars starting today, every Monday, and the theme this semester will be on Iceberg. If you don't know what Iceberg is, it's one of the most important pieces of database technology that's come around the last 3 or 4 or 5 years, right? There's a reason why Databricks paid, I think, $2 billion for it, billion with a B. Snowflake tried to buy it for $600 million. Databricks came in and kneecapped them and took it for $2 billion. Right, so today will be introduction to Iceberg. And then next week will be Hootie, which is the alternative to Iceberg. So both these sort of technology or systems were built at the same time. Iceberg came out of Netflix. Hootie came out of Uber. Iceberg is the dominant one. And then following after that, we'll have Mother Duck give a talk about the Duck Lake system, which is another alternative to Iceberg. Okay? Again, this is optional. All right, so what I do want to cover is the feedback we've gotten through the course. Believe it or not, we get emails and we get messages on YouTube, and we do read them. So the first feedback we got is actually for DJ Cash. So the first guy says, he heard your radio show, which I heard went really, really well, at least from what I heard. He's basically saying, like, you to get more money. Not me, you should get more money. This guy, Sweaty the Glove, says you got the best beats and that he wants to buy your merch. So you're doing that, right? You're releasing something?
We're working on it right now.
You release, what, stickers and shirts or something?
T-shirt, yeah.
Okay, all right, awesome. So that'll be available for DJ Cash coming up. For me, somebody said in the first lecture that I wasn't hyped up enough. I wasn't speaking fast enough so that you can still watch me at 1.25x. So that was surprising. Again, maybe I was down that day, but I get excited and I start thinking really fast. I'm surprised this guy's complaining that I was too slow. And then this guy says that you can't be a nerd or a gangster. You can be either a nerd or a gangster, but you can't be both. I mean, I don't want to comment about my past, but like, was I arrested? Yes. Am I here teaching you guys? Yes. Databases? Yes. So I'm not saying I'm doing something really malicious, but like, whatever. I know a lot of people that have gotten a lot of trouble in life and end up doing databases. So this guy doesn't know what he's talking about. Plus, he's got a photo with his kid. So that's his problem. All right. But one feedback that is actually correct, this guy here pointed out that I made a mistake in, I think, lecture 6, where I talked about how there's this distinction between OLTP and OLAP. And I made the claim that OLAP was coined by Jim Gray. And this guy points out, and he's absolutely correct, that it actually wasn't Jim Gray. It was the other Turing Award winner in databases, although there's 4 of them. So it was one of the other ones, Ted Codd, the guy that invented the relational model. He was the one that was getting paid to write an article about like, hey, here's what OLAP is. And then the article got retracted once they found out it was, he was basically kind of shilling for this company called Essbase, which is a data cube. You don't need to know what the data cube is. It's another way to do analytics for column stores. But this is how people did things in the 90s. And anyway, so he's right that in this lecture here, when I show this picture, it wasn't Jim Gray. It was Ted Cott. Okay. So again, feedback like that is super useful. Maybe not be complaining about me, but feedback for Cash and feedback for the course material is always appreciated. Okay. The last class, we were talking about hash tables. We said these are an important data structure you need in your database system to support various functionalities, various parts of the system. And we spent a lot of time talking about static hash tables. We kind of rushed at the end on dynamic hash tables, so I'll pick that up again and go over that one more time. But most of the time, these hash tables that we're talking about will be used for internal data structures, like things to keep track of, like your page table and so forth, right? Not so much for indexes, which we'll see mostly how they're going to be used in B+Trees today, right? So again, remember last class when we finished off with dynamic hashing, there was essentially there was 3 schemes. There was chain hashing, where you just keep adding things to this long chain. We said, oh, that kind of sucks because now, if in the worst case scenario, you're regressing to a linear scan and you're hitting up ON. So we talked about these 2 approaches: extendable hashing and linear hashing. So I'm going to quickly just go over the example again, and then we didn't get through deletes for linear hashing, so I want to cover that as well. Again, so these are 2 approaches that allow us to reorganize and resize our hash table without having to reorganize everything, right? When we had these static hash tables, when we ran out of space or the fill factor got too big, that we then basically had to make a second copy of a hash table, usually double the size of the original one, and then take all the keys out of the first one and put them in the second one, right? And that's a very expensive thing to do, especially if your hash table is really, really big. So with extendable hashing and linear hashing, the idea is that we can split buckets incrementally and grow them without having to reorganize everything. So in the case of extendable hashing, you have this notion of a global bit counter. Basically, it's the number of bits we have to examine in our hashes, right? So when we hash a value or hash a key, we're always going to get 32 bits or 64 bits. This global marker just says how many bits do we actually need to examine to figure out where to go. And then we had this bucket array that was going to correspond to bits that are the part of the hash values. So in this case here, we'd have some of the bits, or sorry, some of the buckets only require 1 bit, and they end up pointing to the same bucket. And then these other 2 in the bottom are looking at 2 bits. All right. So then when we started doing things like a lookup, a hash on A, we would look at the global bit counter. It's set to 2. So we know we only need to look at 2 bits to figure out where in our bucket array do we need to jump to, right? In this case, 01, we follow that, and we end up with this bucket here at the top, and we find our key. Same thing, now we do a put in B. We only need 2 bits. It lands in this, no problem, that's fine. Now we do a put at C. It requires 2 bits, but then when we follow the pointer, we land up the bucket here in the middle, but it's out of slots in our buckets. So now we got our overflow. So when we do an overflow in extendable hashing, we're basically going to double the size of our bucket array, right? In actuality, you actually usually allocate maybe most of it or large enough size. You're not doubling over time. Also, too, this thing is just not that big, so it's not like the whole hash table. We have the keys and the values and everything else, so it's very expensive to double things. In this case, it's not expensive. So now that I doubled the size, I can split the bucket that overflowed, and then I set now the global counter to 3, and then some of the buckets that weren't split still only require 1 bit. In that case, they're all pointing to the first bucket. The second ones that need 2 bits point to the other one here, and then for the ones that we split before, now they're using 3 bits, and they're now pointing to 2 different buckets. So now when I go back and I want to put C back in, again, now I look at 3 bits, I find the location in my bucket array, and I follow the pointer to the bucket that I want. Okay? So linear hashing was a different approach where instead of splitting the bucket that overflowed, we're actually going to end up splitting the bucket that's where something else is pointing to, this thing called a split pointer. So there was a question last time, oh, this seems kind of wasteful, that like, why are we not splitting the bucket that overflowed? We're just splitting whatever one the split pointer is pointing to. And the idea is that over time, things will sort of balance out. Eventually, you'll end up splitting the bucket that overflowed. And things sort of nicely balance out. All right? Let's go back here. So we still have our bucket array. And now, again, we're not looking at just the bits, just sort of what offset we are in our bucket array. And then we have a split pointer that's just a demarcation to say, what's the next bucket we're going to split? So at the very beginning, it's going to, as soon as we overflow, we'll end up splitting bucket 0. And there'll be some hash function. We just can hash the key, then mod it by n, where n's the size of this bucket array. So we have n at this point where n equals 4. All right, so now I want to put, all right, so I'm going to get 6, hash by 6, just say it's the identity hash, mod it by 4, and I get 2. And then I know how to jump to my bucket array at offset 2, and I land to the bucket that I want. And there's the key I want. Now I want to put 17. 17 hashes to, when I mod 4, I end up with 1. It points to that bucket here, but now that bucket is full, so I have to overflow. But instead of splitting this like I did in extendable hashing, I'm going to extend it out like I do in chain hashing, just add another bucket and maintain a linked list. But then now I'm going to split whatever the split pointer is pointing at. So in this case here, it's pointing at 0. So I'm going to go ahead and split that guy at the top, even though that's not the one that overflowed, but this is just how the algorithm and the protocol works. So now what I'm going to do, I'm going to add a new entry to my bucket array. So now I have a slot 4 at the bottom. And then now I have a second hash key or hash function where I'm going to mod it by 2 times the original one. So before we had n equals 2, and now we're going to mod it by 8. Sorry, by 4, right? Because it's, sorry, n equals 2, because I have n equals 4 in the original one going back here. And then now when I add the new hash function, now it's 2n, so that'll be 8. So eventually I'll have 8 slots in my bucket array, and the split pointers keep moving down, and then at some point it'll wrap around, and then I start the whole process all over again. All right, so in this case here, again, so we're going to take whatever the bucket at the top that the split pointer is pointing at, that we're going to end up splitting that. So we have to look at all the keys that are inside that bucket and figure out, hash them again with the new hash function and figure out where they go. In the case 8 stays where it's at because 8 mod 8 is 0, so that stays at the top. But then when I take 20 and mod 8, I end up with 4, so it lands here at the bottom there. Okay? So it's not like when I do the second hash, because I'm just doing 2n and the new hash function, it's not going to land in any arbitrary bucket. It's either going to be the original bucket or the new bucket I just created. Right? And then the split pointer moves down by 1. And now when I do a lookup on 20, right, 20 mod 4 is 0. So when I do my first lookup, I would see that, this thing for the first hash function is 0. Well, the split pointer is pointing at now 1. So since 0 is less than 1, I know that I've already splitted anything above the split pointer. So to figure out where 20 actually is, I got to hash it again now with the second hash function, and then now I'm going to land the location that has the key that I want. Same thing, get on 8. 8 mod 4 is just 1. 1 is where the split pointer is at, so 1 is equal to 1. So I know I don't need to run the second hash function. I can just jump to the first one and find the thing I'm looking for. Yes?
So the decision of when to use hash 1 or 2 depends on, is it above the split pointer?
The statement is, the decision of when to use hash 1 or 2 is determined based on, it has to do with what the first hash function points at, and it is above the split pointer. So going back here, I always got to hash the first one. I hash the first time, I get 0. 0 is less than 1 where the split pointer is pointing at, so I know I have to go to the second hash function.
Once the split pointer reaches 4 or like past 3, I guess you now abandon hash 1.
The statement is, and he's correct, that say I keep splitting because you keep having overflows, and I'm going to keep adding new entries to my bucket array up until I get to 7, right? And then at that point, the split pointer wraps back around to 0. I can, yes, throw away the first hash function, key 1 mod n, or key mod n, and I'll just have, and then key mod 2n will be the new hash function, or the first hash function, and then I'll have key mod 4n after that. Yes?
So, but how are you dealing with the actual, like, is this just like a linked list or something like?
Yeah, his question is, how do we deal with the overflow? It's just the bucket hashing we talked about before, the chain hashing. So just add a pointer, keep going.
If we put something that maps to 1, is that when we're going to end up splitting again because it's still overflowing?
So his question is, yes, he's correct. So say this bucket here, 1, say it was actually at the bottom, right? And I keep inserting into it and it keeps overflowing. Yes, you would keep splitting anything up above it, the split pointer, because then eventually you'll overflow, it'll get to it and then it'll split.
I'm saying in this case, we already overflowed, right, with the 17.
Yes. So your question is, like, if I insert something again here, does that count as an overflow? Yes. Because I mean, like you could not do it and say, all right, I'll just keep going until that second bucket is full because I've already created it, no big deal. But again, think of it extremes. I don't want to have this really, I have to do a linear scan, jump inside that to find the thing I'm looking for. So if I can avoid that by splitting, it's worth doing that. Okay. So again, this I've already said before. Basically, the idea is that we're just going to keep doing this until, even though we're not splitting the one that overflowed, eventually we will get to this, right? To do deletes, it's basically just the reverse, right? So if I want to delete key 20, same thing. I first do the first hash function. I get 0. I know 0 is above our split pointer. So then I'm going to hash it again. And now I get 4. I jump down here, right? I delete 20. But now the bucket is basically empty. So you could just leave it there if you wanted to. Or you just do the reverse. You could kill it, roll the split pointer back up. And then that 4 slot in the bucket array, nothing's really pointing to it. Nothing can get to it anyway because my hash function won't ever jump to it. So I could just leave it there, right? And the reason why you maybe don't want to clean things up so quick or eagerly immediately as it happens, because if someone now inserts 21 back in, I'm going to be back where I started before and just have another overflow and just do the same thing all over again. So I'm saying in implementations of this, you kind of relax the rules about how quickly you want to revert back on deletes, because you may be doing the same thing over again and you're just spending time moving the split pointer back and forth and reusing space or freeing up space and then allocating it all over again. And we'll see the same idea when we talk about B+Trees today, where there'll be times where so go through what the algorithm says you have to do, but in real implementations they'll relax this a little bit because it'll make a difference in performance. Okay. All right, so let's jump into today's lecture. Again, the beautiful B+Trees. So first, we do an overview on what the data structure actually looks like, and then we'll talk about different design choices you have in actual implementation. And then I'll try to plow through as many optimizations as we can until we run out of time. But I'll cover the main ones that I think are the most interesting, most important ones in the beginning. Okay, so B+Trees are by far the most common data structure you're going to have in databases used for indexes. Like when you call create index in nearly every single data system, you're going to be getting a B+Tree or something that looks like a B+Tree. In some systems like Postgres that support hash table indexes, you have to explicitly say, I want to create table using hash, right? And then because otherwise the default is always using the B+Tree. The reason why is because B+Trees can do any search. You can do point queries, you can do range scans, you can do partial key lookup sometimes. We'll see how to do that. Where in hash tables, you can only do point lookups, like go get this one tuple. I can't do range scans because everything's unordered in the hash table, so it doesn't mean anything. There's no notion of a range where the values aren't ordered. And if I have multiple keys or multiple attributes in my my index key, like table or column A and column B, I can't do a lookup on that index unless I have both columns, right? Because I can't go give me the hash on A and then have that mean anything without B, because I have to have both of those keys together. So B+Tree is going to be way more versatile. So now the tricky thing is going to be is the name is going to be a bit confusing, right? So there's going to be a class of data structures called B-trees, of which there's a specific data structure called a B+Tree, but then there's also another data structure called a B-tree, but the B+Tree and the B-tree are both B-tree data structures, but the B+Tree is not the same as the B-tree. I'll explain what I mean. Okay, so but generally, this sort of category of data structures refer to what are called balanced trees. All right. The original B-tree paper is roughly attributed around 1970. No one's quite sure exactly when it was added, maybe 1969, 1970. And the original paper is basically this one here came out of Boeing, right? And this second author here, McCreet, he's actually CMU alum. He did his PhD here in the 60s, and then he went off to Boeing, and then they were building a data structure. They built a data system, and they needed the data structure, and they basically invented the B-tree, the B+Tree. But the paper most people cite refer to as the original definition of the B+Tree came out 9 years later. There's this famous paper called Ubiquitous B-Tree, right? So again, it's the early days of computing. And obviously there wasn't an internet, so things moved more slowly than they do now. But by 1979, the B tree or B+Tree was considered, the essential data structure we use in data systems. So much it was everywhere, and they were calling it ubiquitous. All right. So the challenge I think is going to be is like there's the original definition of the B tree, the B+Tree, but no one follows what this original papers actually talk about. They're actually going to use bits and pieces of other data structures that are extensions to B+Trees that have come along over the years. And in particular, the one we're going to talk about today as well is called the B-link tree, which actually was invented here in 1981 in Carnegie Mellon. And the first author for this, Phil Lehman, he's still here at CMU. So he's in the 5th floor or the 6th floor at the dean's office, right? The dude's awesome. He's still here. And so when you go look at the Postgres code also as well, they're basically going to be implementing this data structure as well. If you go look in the source code, it'll say for the actual, the B tree data, their B+Tree data structure. So they're going to call it a B tree, but in actuality, is it just a B+Tree? Again, people get fuzzy with the names. But lo and behold, it says right there, this directory contains a correct implementation of Lehman and Yow's high concurrency B tree management algorithm, which comes from this paper written by the dude over there in Gates, right? So again, so Postgres is called the B tree, but it's really a B+Tree. And actually, they're going to call this an NB tree, which is a non-balanced. So they're going to relax some of the things that we talked about before. I'm going to take a guess what the B means in B+Tree. Boeing. Yes, so you've seen the video. Yes, okay. So people think it means balanced. People mistakenly think it means binary. Like a binary B tree is basically where m equals 3. We'll cover that in a second, or next slide, right? But according to Phil, he said he's like 99% sure, 9% sure that when he talked to like the dudes that wrote all these other papers that were at Boeing, he said, yeah, they named it after Boeing because they were at Boeing, right? So, right, so the Boeing tree doesn't sound very catchy, but people just refer to it as the B tree or the B+Tree. So I'll try to be very careful, and I'll make a distinction between what a B+Tree is versus a B tree is. But for going forward, when a database system says they have a B tree, 99.9% of the time they really have a B+Tree. Okay. All right. So a B+Tree is going to be a self-balanced, ordered m-way tree that's going to support the searches, sequential access, insertions, deletions, all the things that we'd want to do in a data structure in log n time, where m is going to be defining the fan out, the number of sort of pointers that are going to come out of each node, which either could be to another node in the tree or could be to the record or whatever it is that we're trying to find. So we define m by that. And so for every node, if you say it's an m-way tree, it'll have m outbound pointers, and that's the degree of the node. But then it's going to have m minus 1 keys that it can reference inside of each node. So it's being claimed to be perfect balance, meaning that the distance from the root to any leaf node will always be the same anywhere out throughout the tree. It means we're going to have to do a bunch of stuff in our data structure to ensure that this is the case. And one of the key requirements is that we're going to say that every single node, except for the root, because it's kind of a special case, or it is a special case, every single root needs to be at least half full, right? And then when it becomes less than half full, we got to do a bunch of extra work to make it be half full by taking keys from our neighbors or merging things together, right? And so the reason why this data structure can be so important, because especially in the early days, but even now with modern hardware, it's going to be optimized for reading and writing large blocks of data very efficiently, right? This data structure is going to convert what would otherwise be potentially random I/O into sequential I/O. And as we said in the beginning, that's going to make a big deal when it comes to actually constant time factors for actually running our system, right? If we can maximize the amount of sequential I/O, then we're going to get better performance. And as I said, some systems implement the B+Tree will relax these properties, but we'll ignore that for now and go strictly by this definition. I'll say also too, the fan out is going to be pretty large, right? So m is usually a large number. Think of like an 8 kilobyte page in Postgres. I can put a lot of key values in pairs inside that thing, right? So the height of a real system of these data structures, a B+Tree, it's going to be like maybe 4 or 5 levels, because the fan out is going to be quite large. But in case of PowerPoint, I have to make it fit. So we'll look at simple examples here. So this would be a 3-way tree. So there's going to be the fan out is 3 for every node. So I have 3 pointers coming out, and I'll store 2 keys inside each node. So at the top, we have the root node. The middle layers we call the inner or non-leaf nodes. And then the bottom nodes we call the leaf nodes. The way to think about this is that along the leaf nodes, our keys are going to be sorted from, in this case here, low to high. You can define you want it to be the opposite. You can go high to low. But these are going to be sorted according to some correlation ordering that we would define in our database system. So the contents of the nodes for the root and the non-leaf one, the inner nodes, is going to be alternating key value pairs of some kind of pointer to another node in our data structure, followed by a discriminating key that's going to allow us to determine whether we want to go left or right to find the entry that we're looking for. And then in the leaf nodes, these will be key value pairs where there'll be the actual key that we want to find, and then its corresponding value, which could be a pointer to some data structure or something else, or it could be the record ID. In the case of other systems like MySQL, could actually be the entire tuple. For our purposes now, it doesn't quite matter. So the way to understand these keys, they're basically in the inner nodes in the root, they're guideposts that allow us to figure out where we want to go when we do our traversal into the index. And so for this example here, I'm going to say I have my root node, I have key 20. So if I want to go to our left, there'll be all the keys that are less than 20. And then on the other side, the right, there'll be all keys that are equal to or greater than 20. So for any given key, I can just look at that, look at that node, look at the key, and decide whether I want to go left or right. One thing we're going to also add as well, and this will make it easier for us to do splits and merges in a second, is add sibling pointers. This is what the B+Tree in 1981 added for us. So now when I want to do a lookup like a range scan, like find me all the keys that are greater than 15 or greater, I could go start my root node, traverse down to the bottom, and then now scan across to on the leaf nodes and follow those sibling pointers to find all the entries that I want. And I don't have to backtrack and go back up to my parent to jump down to the next one. Yes. The question, yeah, yes. Sorry, what is the question? So what are the values of M? So I mean, N is just the number of keys at the bottom. You would count those. But M would be, and in this case, there's 3. Because for every node, right, going back, say the one at the top, right, you have node pointer, tells you how to go down to one side. You have the key, the discriminating key that tells you whether, whether you want to go left or right based on the value of it, followed by the next pointer. Yes?
For range query, I don't see why you would need sibling pointers in the non.
The question is, for range pointers, you don't know why you would need sibling pointers in line leaf nodes. You'll need them for splits and merges. But for once you reach to the bottom, if you're just reading, you never have to go back up. Yes? Question, in that root node, there's 3 node pointers? Yes. Why what? So the question is, why do I need 3 node pointers if I'm only pointing to 2? How am I allocating this? Think in a real system. What's the backing memory of this? No. What's the backing memory of the data in a node? Like, I'd have to store the node, the contents of the node somewhere. What am I storing it in? What is it? A page. Pages are all fixed size. So in my PowerPoint example, yeah, I have 2 pointers coming out of it. But in a real system, I'm going to allocate a 4 kilobyte, 8 kilobyte page. I'm going to allocate the space for it. So it's always going to be there. Because his question is, why did I just what I just said explain what there's 3 pointers? Because it's not like an in-memory data structure where I'm just calling malloc and I only get the data that I actually need. I'm going to go to the buffer pool manager and say, I need a page, right? And you're going to get back an 8 kilobyte chunk of memory. So I'm going to allocate the space for it. In my diagram, yes, the space is not being used. In a real system, you would have that space allocated anyway, even if it's still not being used. Okay, so on the leaf nodes, I'm just showing that we'd have pointers for siblings on the backside of the array, right? So at its core, what is the B+Tree? What are we doing? He says binary search tree. Over what? Yeah, but what's the data structure at the bottom? What is this? Not a hash table, linked list, right? So all this data structure is, and all these tree data structures is, just allow us to jump into our linked list more efficiently. Because otherwise, without this stuff at the top, what do I have to do? I got to scan along linearly on the leaf nodes to find the thing that I want, right? So, oops, sorry, go back. So it's not that exotic. If you just think about the top part is just this scaffolding we're going to build up on top of this linked list so that we can jump to the bottom to find the thing that we want or the keys that we want. All right? Skip list, basically the same thing. Tries a little bit different, but you know, in the end of the day, that's what this data structure is doing for us. It allows us to jump to locations in our linked list without having to scan from beginning to end every single time. Again, because always think in extremes, right? If I have a billion keys or a trillion keys, I don't want to do that linear scan every single time. My B+Tree will allow me to jump into it. And as I said before, the fan out will be quite large in a real system, so I'm only going to have to jump down at most maybe 5 levels. And I can represent a lot of keys in my leaf nodes. All right, so the leaf nodes themselves, the nodes themselves are just, think of the arrays of key value pairs, right? The values that we're going to be storing are going to be different based on whether we are an inner node versus a leaf node, right? If it's an inner node, the values are going to be pointers to other nodes, and these are just page numbers, right? That I can do a lookup on the buffer pool to go get the data that I want. And then the leaf nodes will vary based on what I actually want to store. Do I want to store record IDs to pointers to tuples? Do I want to store the entire tuple itself, like I do with MySQL and SQLite? In some systems like MySQL as well, the leaf nodes will actually store a primary key as the values. So then I can take the value, the primary key, and do a lookup in the primary key index to actually get the record ID or get the table, right? And then for nulls, we have to treat them specially, and typically you either put them at the beginning of the list or at the end of the leaf nodes. Right? I think by default in Postgres, they put them at the end. So again, I'm showing this sort of diagram like this in my before, because it has to fit in PowerPoint. I'm showing these sort of key value pairs over and over again. In actuality, a real system wouldn't actually store it like this. You would have some extra metadata that you would store at the top. They say like what level I'm at, how many slots can I store, what's my previous pointer and next pointer. Sometimes there's additional metadata say like how many keys do I have inside here, what's the high key, what's the max value I can store in my page. Some extra things that make me find data more quickly. And then you could store the example I was showing before where you just have the key followed by its record ID, or sorry, the pointer right afterwards as the value. In a lot of systems instead, what you do is you store all the keys sorted as a separate array. Then you store all the values just in a fixed length array or some kind of array that you can then just jump to offsets like we did in the column store based on whatever key that I'm looking for. So now I can, if I want to find the key that I want, I can just do binary search on the key array and not have to jump over data that I actually don't need. Yes?
I still don't get the relationship between a node and a page. Is one node, one page?
The question is one node, one page? Not always, but you could, for simplicity, think of it like that, yes. But if the database page is 8 kilobytes, the node is going to be 8 kilobytes. That's what I'm saying. The fan out's going to be quite big because you can put a lot of key value pairs in 8 kilobytes. What's that? This question is, when will it not be one page? Give me a few more slides. Sometimes my keys can be quite big and I got to overflow. This question is, how do you maintain sorted keys? I don't know, pick your favorite sorting algorithm, quicksort. Right? It's in memory. This question is, does that mean whenever a key is inserted, am I going to resort it? In most systems, yes. You don't have to. But in general, yes. But again, like it's in memory. I'm already reading it, so I hold the latch on it, the mutex on it, so I can do whatever I want once I have that. This question, that's a lot of movement. This is going to fit in cache lines. It's not going to be that bad. I can sort 100 keys pretty quickly. Yes, sorry. Question is, keys be variable length? Yes, we'll solve that. Give me a few more slides. Yes, that makes it harder. All right, so I've already said this. What are going to be the values in our leaf nodes? In most systems, it'll be the record ID, and it's like a page number and an offset, and that's going to be always fixed length, and that allows us to jump to find that we want. In other systems, it can actually be the tuple themselves. We saw this in index organized storage. in MySQL and Postgres and Oracle and other systems, right? MySQL and SQLite give you this by default. Like when you create a table, you get it. In SQL Server and Oracle, you have to explicitly say that I want it. All right, so now that you understand the basics of B-trees and B+Trees, or you know the basics of B+Trees, let me make the distinction of what the difference between a B tree is and a B+Tree. Actually, this should be 1970, not 1971. But in the original B tree, all the values could exist anywhere in the inner nodes. Meaning, if I'm doing traversal to find the thing that find the key that I want, I may hit the first root node, and then I'll find the key that I want, and then I get the value right then and there. In the B+Tree, the values, again, like the record IDs or whatever it is that's actually representing the data of the tuple that I'm trying to find in my data structure, only exist in the leaf nodes. So in order to find whether a key exists, I always got to get down to the leaf node. And it's either there or not there. So B trees are going to be more efficient in terms of space, but I now may have to do this depth first search and jump up and down and come back up to the root over and over again to try and find the thing that I want. And that's going to be random IO. That's going to be bad. In the case of a B+Tree, once I get to the leaf nodes, ignoring splits and merges, once I get to the leaf nodes, I'm trying to find data. I can do sequential scans to find the things that I'm looking for. And that's a key distinction. So when we delete a key now, it may, in a B+Tree, it may still exist in the inner nodes, but it'll get removed from the leaf nodes, and that's okay. In a B tree, if we delete a key, it has to be completely removed from the tree. Red black trees work the same way. All the other ones work the same way, but they're going to be, they're going to have their own issues, right? So B+Trees are going to be slightly larger than B trees, but we're going to get better performance because we do more sequential scans. And actually, we'll see in 2 weeks or next week, when we start having multiple threads jumping into our data structure, B+Trees are going to be way better than a B tree. All right, so let's first talk about how we want to do insert. So the protocol, as I said, for doing a lookup is, again, you just look at the keys, figure out where you want to go left and right, and then jump down and keep going until you find the leaf node, and you either find the data you want or you don't. Now to do an insert, we're going to do that same lookup procedure where we're going to traverse the data structure, find the leaf node that should have the key that we want to insert, and then go ahead and try to insert it. If there's enough space in that leaf node, great, we're done. If there's not enough space, meaning that all the array is full, then we have to do a split. And that means we in this case here, we will now redistribute our keys that are in the node that overflowed to other nodes, which then may require us to then do a bunch of splits going up the data structure. So upon insert, we may have to reorganize the entire tree in the worst case scenario, but in most of the cases, most cases we'll have enough space in the leaf node we're trying to insert into, and then worst case scenario, we'll have to then maybe split our parent, right? And then the split process, we're just going to redistribute the keys evenly by just taking whatever the middle key is and using that as the halfway point, split things in half, and then push the middle key up as a discriminator in the tree above us, and recursively do this until everything's balanced. So going back to a really simple example here, now we have again a 4-way tree with 3 keys. So there's four branches that could come out of every single node, and then we have our sort of our ranges here. And now I'm showing like just 4 greater than or equal to 4 and less than 12. Like here's the more compact form of that, right? So say I want to insert 6. So again, I started my root node. I look at the keys that I have there. 6 is greater than 4, but less than 12. So I know I want to go down to this leaf node here. But this node is full, so I have to split it. So what I'm going to do is I'm going to end up creating a new node, a new leaf node that's currently empty. Then I'm going to take half the keys in my first node, or take all the keys, figure out what the middle point is. Half the keys are going to go in the original node. The other half of the keys are going to go into the other node. So you would end up like this, right? The 6 went into the original node, but 9 and 10 got moved over to the other one. Am I done? No, right? Now I got to go back up to my parent and add a key there to make sure that if anybody's looking for 9 and 10, they know how to go find it. So in this case here, I can just choose the smallest key on this node here, 9, is basically what I split on before, and put 9 at the top there. And at this point, I'm done. Right? And I just update my, well, you wouldn't store the ranges like here. The keys essentially are giving you that ranges. Right? Because when you traverse the tree, you know how to interpret the contents. Okay? Yes?
And you don't remove the 9 in the bottom, then the leaf.
The question is, you don't remove the 9? Why would you do that?
I mean, you move the 9 up to the first in the root.
Statement is, why don't I remove the 9? Well, then if the key exists, it has to exist in the leaf nodes, right? So going back here, 9 was in here before, right? 5, 9, 10. So 9's in there.
Any key must exist in the root node, in the leaf node.
Statement is, and he's correct, any key that exists in my data structure has to exist in the leaf nodes? Yes. His question is, why isn't 4 there? Because 4 was inserted and then got deleted. That's okay. In a B tree, you can't do that. In a B plus tree, you can. All right, let's do another insert. Let's now insert 8. 8, again, root node, we followed the pointer. 8 is less than 9, but greater than 4. That takes us down here. We go ahead and insert, and that's fine, right? And let's look at a bigger table. So I want to insert 17. 17 should go here. That's fine, we can absorb that. Now I want to insert 16. 16 should go between 15 and 16, but there's not enough space in here where I can store it. So I want to split the node again. So essentially I'm going to create a new node and then shuffle all the keys from the new node that got overflowed. Put half on one, half on the other, right? So say I split on 16, so everything 16 or greater goes to the new node. Everything 16 less stays in the original node. But now I have to update my root parent, in this case the root node, to now add 16 there, so anybody that's coming down can find us. But of course now the problem is our root node is full as well. So you recursively go up and keep trying to insert new keys back up. And if you have to split your parent node, you got to run basically the whole protocol again. And as you go up from one level to the next, you don't reorganize anything below you because you've already handled that, make sure it's balanced. But as you go up, you make sure everything else is balanced until you reach the root and you're done. So in this case here, our root node is full. So we're going to split it again and then grow the tree and make it taller. So 13 is going to get moved up because that'll be the middle key for our for the new root of the entire tree. And then 16 is going to get put where between 9 and 19, right? But now what we need to do is split this, because anytime I've inserted something up, I have to split whatever node that's got overflowed. And so I'm going to create 2 new nodes here. Well, you just copy. You create a new one and then reallocate things in the original one. That's fine. And then now I update my my root node, the new root node on 13, to now point to values less than 13, which is 5 and 9, and values greater than 13, which is 16 and 19 on this side, or greater than equal to 13, which is 16 and 19 here. So the new organization of the discriminator keys looks like this. Yes?
Is there a reason why when we initially try to insert 16, we don't just move stuff to the left? Because like if you go at the very beginning when we try to insert 16, like in the node on the left, like the node with 9 and 11, there's just space here, right? Like
Yeah.
you just move 13 and 14.
Yes, so he's talking about optimization, and we'll see this when we do deletes. If I'm back here, I want to insert 16. I can recognize, oh, well, the guy on where node 9, 11 are, or even 20, 21, 23, they can absorb one more key. So I could follow my sibling pointers and just shuffle things around, move 13 and 14 over the other one, and then put 16 on this one. I wouldn't have to split it. You could do that. It's basically what you do when sometimes deletes and other things. It's just more machinery, right? It's an optimization, like I'm trying to do the basics first. But yes, you could do that. And it still would be correct. Right? And then the question always people ask is like going back here, right? At this point here, why not just say we're done here, right? Why do I have to create a new node at the second level? Because then it's actually no longer balanced, right? It doesn't follow the protocol where you have exactly, it's still the traversal is still correct. But from the top point, from the roots node perspective, all of the keys are on one side of it, not the other side. So it's not considered balanced in that way. So So that's why we always have to split whatever the level that's overflowed to create new nodes and then reconstruct the tree like that. And again, since these are all backed by pages, if all the keys on this side of the tree were out on disk and not in our buffer pool manager, or not in our buffer pool, we don't have to bring them in to do anything because we're just updating pointers to the page IDs for the other parts of the tree. And so the nice thing about this data structure is that we just, if there's parts of the tree that we don't need while we're reorganizing things, they just can sit out on disk and not bother anybody and not take up space. All right, so look at the deletes. Deletes are basically the opposite of this. Again, the idea is that when we delete a key, if after the deletion of a key from a leaf node, it's still at least half full, congrats, we're done. We don't do anything, right? If, though, deleting that key now makes us less than half full, we can first try to redistribute and rebalance the data structure in the way he was suggesting by trying to stealing keys from our siblings so that we don't have to reorganize everything all over again. But if stealing a key from an adjacent node, and usually you only look at the one guy over, you don't try to look at all your siblings. If you can steal it without rebalancing, you're done. If you steal a key from either one of your siblings and makes them less than half full, then you have to do a merge. In which case you'll end up deleting a key, a discriminator key on your parent above you, which may again recursively go all the way at the top and cause you to rewrite the entire tree. All right, so let's hear it. We're going to delete key 6. We go ahead and delete that, do traversal, right? Now we're less than half full after that. So we can try to borrow from a rich sibling, being a sibling that can absorb a delete from us and still be more than half full. So in this case here, we can take 9 from our sibling, go ahead and put that in our data structure, but now we need to update our parent pointer or parent key for the discriminator, because anybody looking for any value greater than or equal to 9, as in this current form of the tree, would end up falling to along the right side and at least this leaf node, and then completely miss the key and think it was actually not there when it actually was there. So we got to go up and update that guy here by putting 12 there. And then now our tree is considered correct. Yes?
So in like a production system, if you're going to do something like this, would you store metadata about the number of children in the number of entries in the leaf nodes, or would you just scan over for a count?
Oh, wait, so you said for in a protection system? What do you mean? Sorry.
Production system.
What's that?
A production system.
Oh, production. Sorry. Oh, yeah. This question is, how do you find out whether you can steal keys from your neighbor?
You said the fan out's like going to be really large.
Yeah, so they're saying you only look the next door neighbors. You don't try to look at all the possible siblings. You could, but it's just like now you're taking latches, which again we'll talk about next week. You're just taking more locks and taking latches, not locks. Taking latches, and that just can slow everything else down. Yes.
You said also earlier that each node has pointer to its sibling or neighboring.
Yes. Yes. But for simplicity, we're just assuming leaf nodes. All right, let's look at a more complicated example. So I'm going to delete key 15 here. So again, if I delete key 15 from this node, or when I delete key 15, the node is less than half full. So I can steal from a rich sibling, right? And then 17 goes over there. Update the parent now to put 19 there, and now everything is all kosher and correct, right? So that's fine. But now I want to go ahead and delete 19, right? So go ahead and I delete 19, and I want to try to see whether I can steal from one of my neighbors, and I can't. Because if I take either from 1317 or 2123, if I take from any of those nodes, they'll be less than half full. And then now that's not balanced, and we got to fix that. So in this case here, we don't have a choice. We're gonna have to do a merge, right? So we're gonna merge from our neighbor to our right. You could do it from the left. Different systems do different things. It doesn't matter, right? Long as we sort of go one way, it doesn't matter. Actually, I think you go both ways. For simplicity, most people go one way. All right, so we're going to go ahead and merge these guys. So in this case here, we're going to basically take all the keys 21, 23 and put it in the node where 20 is located here. And we have to then delete the discriminator key in our parent because we don't need to point down now to this other node that doesn't exist anymore, right? So after we do this, our leaf nodes are all balanced. That's fine. But now this parent node is less than half full. So now we got to do this. We got to do a we have to do a merge. And essentially, to do this, because it's the root, we can pull the root down here, merge these guys together into a new node like this, right? And the height of our tree has shrunk. And then all of the discriminator keys correctly point to the pages that we want.
The pull down is actually like first emerge from the sibling, and then you detect that the root is underfilled.
Yeah. So this question is, what do I mean by pull down? Yeah, you would see, well, this guy's under full. If I take my sibling, following that sibling pointer I'm just not showing in the diagram, then that guy would be under full. So I have no choice but to go up. In this case here, it's the root. So therefore, I know if I can bring it down and then collapse them together into a single node. But point out here. So I deleted key 19, but I still have key 19 in my inner node. And again, in a B+ tree, that's okay, because it's just a guidepost to tell us where to go find the things that we want. You wouldn't actually say, oh, I got key 19 in the inner node. I'm looking for key 19. I'm done. You always have to check the leaf node to see whether it actually exists or not. So it's okay that key 19 is in there already, which means that we can throw away anything we don't need in our inner nodes when we do this compaction or merging, because, again, we're not throwing away real data. Long as our discriminator keys correctly point to the parts that we want in our leaf nodes, it's okay for us to go from 5 keys to 4 keys. Yes?
So the root has been underfilled from the beginning.
His question is, has the root been underfilled from the beginning? In this example, yes. The root is like special case. You can kind of let that go less than half full. That's usually how it works. Yes?
If the node with 5.9 was full, would we have to do kind of a redistribute operation?
Yeah, his question is, if the node 5.9 could handle taking sending a key over to the sibling, would we have to redistribute? Again, you wouldn't have to touch the leaf nodes, right? All you'd have to do, say there was key, I don't know, 4, 5, 9, and I send 9 over, right? All you need to do is drop the pointer from I don't want to use the laser pointer. Drop that pointer here, get rid of this, then now you have a new one point to that, and that's all fine.
Move on.
Yeah, that's fine. Okay. Well, if you follow this so far, congrats. This is the B+ tree, right? Of course, the devil's in the details. Implementing it will be challenging for project 2, but the gist of it is pretty straightforward. The challenge really comes to be when you start having to do concurrent access of doing splits and merges while other threads are trying to read and write data at the same time. That's where things get tricky. All right, so I sort of mentioned this before, that the great things about B+ trees is that you can use composite keys or composite indexes, use them as composite indexes, which basically means you have a key that's comprised of multiple attributes. So I can create a table create an index on table XXX, and in here you can see that I have I'm using 3 columns, A, B, and C, for my key, and I can also specify additional metadata about like what should be the sort order on a per key basis, or whether I want the nulls to be first or last on a per key basis, right? And then now in a B+ tree, because I'm not hashing, where I'm sort of randomizing the keys, I can do a bunch of different lookups on having either the entire keys or all the keys, or a subset of the keys, and everything just all works. So again, I have an index on A, B, and C. I can do a lookup on A and B and C, or an index on just A and B. And then some systems, Oracle and now Postgres now has this too. You can do what are called skip scans or partial keys, where I don't have the prefix, I don't have A, but I can still do lookups on B and C. There's extra machinery to make that work. We'll see that in this slide. Okay, so again, say I have a key on A and B. And so again, you see that the keys now are comprised of multiple things. And these are just the bits stored sequentially after another. They're not there's nothing that's really special about it. And because it's all declared in SQL, I know what the size of the data type I'm trying to store is. So I know how to interpret like a byte array as the first 32 bits is an integer for key A, and the next 32 bits is an integer for key B. Right? All that you know because it's in the catalog when you created the table or created the index. So if I want to do a lookup on key 1, 2, or A equals 1 and B equals 2. So again, I just jump to the first node. I look at the first key in my composite index or composite key, 1 is less than 1, and then 2 is less than or equal to 3, and I know how to then jump down to the leaf node to find the thing that I'm looking for. So that's when you look up when you have all the attributes, the full lookup. If you only have the first key and not the other keys, like a prefix lookup, then, well, in this case here, I just do the lookup for the first key that I do have. 1 is less than or equal to 1. I then jump down to this leaf node here. But now, since I don't know, since there may be multiple keys or multiple key value pairs in my leaf nodes where the key A equals 1, I have to scan along the leaf nodes until I find the first entry where key A does not equal 1, right? So in this case here, I would come across the second last key, the next key in this leaf node, the key A equals 2. I know that doesn't equal 1, so I can stop scanning there and not have to look at anything after that. All right, so I can do a sequential scan along the leaf nodes and find everything I want. And the last one, as I said, you can actually do a suffix search, or Oracle calls them skip scans. Basically, it says like, I don't know what's in the prefix of my key. I don't have that. I only have the second part, right? So I don't have A, but I have B. So in this case here, there's nothing really magical you can do. You kind of got to look at everything, right? You got to look at all the leaf nodes, but you can do this in parallel. They can all scan across leaf nodes until you find all the matches that you want where B equals 1. Because again, it's sort of this key is first sorted on A, then B. So all the A's, A equal 1 is going to be on one side, then 2s and 3s and so forth. And then the B values are kind of they're sort of within each subset of the A values. Like a group by with multiple columns. Yes.
So does the query engine automatically reorder the keys when there is like a potential prefix in your query condition?
What do you mean by reorder the keys?
So, for example, your index is like key A and then key B. If I write like B equals 2 and A equals 1, where will it be smart enough to reorder the A and B?
The question is, do I have to specify in my SQL query, my where clause, the keys in the same order that the index is defined on? No. Again, it's declarative. SQL says I do a lookup on A equals 1 and B equals 2, right? I can do B equals 2 and A equals 1. Semantically, they're the same. Just because you wrote them in that order doesn't mean I'm going to run them in that order, right?
But are the query engines actually smart enough to see that?
The question is, are the query engines actually smart enough to see that? The good ones are, right? But most of the ones you can think of, like Oracle, Postgres, MySQL, all of them are not. They'll do it, right? When we talk about join ordering, there's a bunch of systems. So join ordering, you basically want to figure out the right way to join tables, and that one you can have a huge difference in performance. There's a bunch of systems where they'll go in the order that you define in the SQL query, and they don't try to do reorder it for you. The good ones say, like, I don't care how you defined it. I'm going to figure out the best way to do it. Right? So Oracle used to do that. Oracle in the 80s, we'll cover this later, used to say, oh yeah, no, we're going to give you a query plan in the order that you define the tables. Because they call it a semantic optimizer. It's all bull. It's like, oh, this is the order you meant it to be in, so we're going to run it that way, even though that wasn't actually what the right way to do it is. We'll cover this later. Yes. There's a lot of systems, for getting this right, it's not hard. Join order is the harder one, and some systems will cheap out on that. Okay. So, all right, duplicate keys. So we've talked about primary key indexes. Primary key indexes have to be guaranteed unique, right? Primary key has to be guaranteed unique. You can also have secondary indexes, where again, you can define that the secondary index has to be unique on the keys. In actuality, though, a lot of systems actually still don't store things. They still will have duplicate keys, because you may do multi-versioning. We'll cover that later, but I may have multiple versions of a tuple that are all going to have the same primary key, and I got to put this in the index in order to find them. So how do you handle that, right? Or think of like people, if you have an index on the zip code for people's address, mailing address, there's a bunch of people that live in 15217, 15213 in Pittsburgh. So I can't have how am I going to handle having duplicate keys in that case? So there's two ways to do this. The first one is the right one. The second one, don't do this, right? So the first one is you basically store a hidden value, or sorry, hidden attribute in the key of the index, that's going to be the record ID of the thing I want to point to. Remember, the record ID is like a page number and an offset. It's a guaranteed to be physically unique for every single physical value. So even though I'm going to declare my index on the zip code, I'm actually storing the key. I'm also going to store the record ID, and it's be hidden from you as the end user. You can't see it through SQL. And the reason why B+Trees are going to work for this because we can do that prefix scan. Because if I have a index on A and B, but I only have the value of key A, the first part, I can still do lookups on it. So now I can do my lookup on the zip code without having your record ID and find all the entries correct, find all the entries that I wanted. The alternative is to do overflow leaf nodes. Now, we'll see overflow nodes that handle large keys, which you kind of have to do. There's no way to get around this. But if you want to handle duplicate keys, you could overflow on the leaf nodes. Don't do this, even though it's going to look very similar. One is sort of, this is all semantics, like one is sort of overflowing down versus across. Don't do the down one, do the across one. It'll make more sense in the next slide. All right, so the first one, append the record ID. So the key now is going to be whatever the real key is I define, like on column A, but also in that same byte array for that key, I'm going to store the record ID. Right? And that'll be guaranteed uniqueness because there's only one physical tuple that can be at some physical address in my pages at an offset. So this guarantees uniqueness, even though I may have the same key over and over again. So now I want to do keys. So I'm going to insert 6 in my data structure, my B+Tree. What I'm really doing is inserting 6 followed by the page number and the offset. And then now I just do the traversal down looking at the first key where it's 6. Then I land into whatever the leaf node that I want and store the thing that I want. In this case here, I have to do a split, right? And everything works out fine. If I want to do an overflow node, so I already have key 6 in my data structure. Now I want to insert 6 again. So I traverse down. I end at this leaf node here. See that it's already full. So I'm going to add another page to it and just maintain like a linked list going in the vertical direction, going down. Violates that log n lookup because now I have to jump to this one and maybe keep scanning. But it's sort of like the chain hash table where I can just keep adding buckets my chain, right, in order to accommodate when I have overflow. It's basically the same idea. I'm going to start at 7, so forth, same down here. So in this case here, I can absorb a bunch of writes into this overflow leaf node here, and I'm not changing any of the discriminator keys in my inner nodes up above. Insert 6, you do the same thing. Right, the reason why this is a bad idea is because if I need to now do a split, right, because I want to insert say key 7.5, that logically should go between 7 and 8. Now I got to do a split, and now I got to remove all this other crap down below as well. I have to scan them all, bring them all into memory, figure out where they need to go, and split them up. And they now may have overflows on both sides or both the new pages. Yes. This question is, for this one here, because 6 already existed, am I only inserting the page number and the slot number and the new key I'm inserting, or all the keys? It has to be all the keys. Okay, the question is, do you change the B+Tree for all the keys? Yes. Postgres does this. Most systems have to do this. Okay. So clustered indexes are basically the idea. Sometimes you hear things referred to as cluster index or a cluster table. This means a sorted table, and it's going to be sorted based on some B+Tree up above, right? You can't use hash index or hash table because that's not sorted, but it'll be B+Tree up above. And so if you do index organized storage like MySQL and MySQL and SQLite, you get this for free because the leaf nodes are sorting the data based on the primary key up above in the inner nodes. In some systems, you can create a table using heap storage, so unordered tuples, but then you can tell the data system, oh, by the way, manage this, make sure things are sorted based on this other data structure here. And in some systems, they'll maintain it. So if I insert new things, it'll make sure everything's still sorted. In other systems like Postgres, you can call it as a cluster command. It'll sort your table based on some index, but it'll do it once. And then if it's updated and changed over time, it doesn't maintain the sort order. You got to run the cluster thing again. So the reason why this matters is that it's going to make it can make our lookups more efficient in many cases, right? If we have to go to get things from disk. So if my table pages are sorted in the same order that's defined by the index, then when I want to do a scan and try to find data, I can just, again, use my index to find some offset within or some location at a table page, and then scan along the rest of the pages, and I'll find everything that I want. Where things can go wrong is that if the index is going to define one sort order, but then the data is going to be sorted in another sort order, I may have really inefficient access if I naively retrieve whatever the page is that the index is pointing to one at a time. So let's say I'm trying to find some range of data between these pages here. And so if you look at the pointers in or the record IDs in my index, the leaf nodes, they're basically pointing to all different locations in these different pages. So if I do a sequential scan, just starting at whatever the first key that I want, and then just go get that data, and then go look at the next key in the order defined by the index, I'm going to start jumping around at these different pages over and over again unnecessarily. So if you think of like a really stupid system only had like one slot or one frame in our buffer pool, I would read page 102, throw that away, then read page 103, throw that away, and then read page 104. In which case here I have two keys that are both in page 104. I can read it, read that page, use that page twice, right? So in a bunch of systems, a simple optimization is you'd actually first do a scan on the index, find all the record IDs and the corresponding page IDs that you know you're going to need to access, sort them by the page ID, and then now go retrieve them in that sort order. So that guarantees I'm only retrieving each page once and only once. I still have to maintain some metadata to keep track of like what's the key sort order that came out of the index, but I'm basically going to scan the index first, figure out what I need, then go get it. And you can start playing other games. We'll see next class or in a couple weeks where like if I have like where A equals 1 and I have an index on that, and B equals 2 and I have a separate index on that, I'll do a index scan across them both, then do a intersection of those two lists of page IDs to figure out what's the minimal set that I actually need. Then go get those pages. Postgres calls this a bitmap heap scan. So we can use these indexes to help us be more intelligent about going get the data that we need to avoid random I/O. All right, so let me get through the node design choices. And like I said, I want to plow through as many optimizations as we can. These ones are pretty straightforward. And again, just to reiterate how important this data structure is just for humanity, right? There's a book written about 10 years ago on modern B+Trees. So here's like a data structure from the 1970s, but here's all the modern incarnations and optimizations you can do to it to make these things go better. And again, it's so important that they wrote a second book that came out last year on more modern B+Trees. And the guy that wrote this is, we're going to see multiple times throughout the semester, that he's going to invent the iterator model of the Volcano process query processing model. He's going to invent the way we want to build query optimizers. He's going to invent the way we're going to do parallel operations in our database system. So this guy is brilliant, and he's written the definitive guide on B+Trees. Again, notice though he calls them B-trees instead of B+Trees, right? But it's the same thing. All right, node size should be pretty obvious that you can have different node sizes for the inner nodes versus the leaf nodes. Typically, you want to maybe have larger inner nodes than leaf nodes, assuming you're not storing the tuples themselves or just record IDs, because then you can have within one node, you can have a higher fan out and find things more quickly. And then, of course, the size of the node is going to depend on what the hardware looks like. So the way the research basically plays out is that if your hardware is very, very fast, your storage is very, very fast, like in memory, then you actually want really small node sizes because you want to be able to go acquire the latch on one small page, find what you want, and what you can do quickly, immediately jump out of that. But if your hardware is slower, like a spinning disk hard drive, then you want your node sizes to be maybe 1 megabyte. So in a system like Postgres, you can't vary the size of index pages, but in enterprise systems like in DB2, Again, you can specify different page sizes on a table basis and on an index basis. And I think they can even discriminate between the inner nodes and the leaf nodes and have different page sizes for them. So the merge threshold we talked about is like if it's less than half full, then I have to do a merge or try to steal from my sibling, right? If you follow exactly that protocol, then you roughly end up with the occupancy rate of about 69, 70%. So about 70% of your nodes are going to be full at any given time, right? So if you can delay the merge process as long as possible, then you can avoid some unnecessary disk I/O because you're not in the situation where I'm merging and then someone immediately inserts something and I have to split again. So you want to let things kind of go a little less than half full for a while. Eventually, maybe say, oh, I'm not using this space. Let me go ahead and clean it up. But it'll allow you to handle more inserts without having to do additional splits if you don't relax this right away. And so it ends up being not exactly balanced anymore. This is why the Postgres B+Tree implementation is called a non-balanced B+Tree. So overall, it's balanced, but sometimes it's okay to relax that. All right, the next question is how to handle variable length keys. So there's a bunch of ways to do this. One optimization is just to store pointers. So instead of actually storing the actual variable length key in my nodes, my pages, I just have a pointer, the record ID, to the actual tuple with that attribute I want. Because I already knew how to store variable length data in my table pages that we talked about before. So instead of storing that in my tuple pages, I'll store a record to it. Yes? So actually, you still need the key to range search. You got to follow the pointer to go get the key to figure out how to do the range search.
Every time you go to the point to get the key.
Yes. Yes. Yes, go ahead.
Isn't that like way more random access?
Yes. So don't do that. So this shows up in memory database systems in the 80s. There was a system from Oracle called times 10 in the 90s that did this. The basic idea is like, oh, memory is so precious. Instead of storing these redundant keys, because essentially the index is storing another copy of data, right? It's like a secondary copy of the data that's in your tables. So instead of storing the secondary copy of data in my index, if I can go get the data very quickly because everything's in memory, then I'll just store the pointer to it. Turns out though that random access still sucks in memory, as well as definitely on disk. So nobody actually does this, at least I'm aware of. Like Oracle still supports this in times 10. By default, you went back to B+Tree. You could have variable length nodes. Basically allows the size of every single node could be arbitrarily different size. Usually you do like sort of almost like a slab allocator. You have like a 1 kilobyte node, a 2 kilobyte node, 4 and so forth, right? This one, you can do it. It only shows up in academic systems because it requires more memory management because now the frames in your buffer pool manager could be different sizes and you have to be able to handle that. You're basically re-implementing malloc in your database system, which may not be a good idea. A cheap out would be just padding, so you know the max size of any given key. Like it's going to be 32 characters, so no matter whether it's 32 characters or something less, you just pad it out with a bunch of zeros at the end so that things always nicely fit. The implementation that everyone usually does is that you just have the same way we have slotted pages, where you could have you take a page and sort of the data is growing from the end to the beginning. You can do the same thing for your variable keys. So then now you have an offset array to say, for a given key, here's the offset within my page to find the actual key that I want. So the last one is usually what people do. And then if you have really, really large keys that don't fit, then you overflow horizontally. And that's okay. All right. How do you find the data within a node? So the first most obvious thing to do is just do linear search. So I want to find key 8. I got to find it in my array. I just start from the beginning, scan across until I find it, and I'm done. Again, it's not the full table, or not the full data set, so this is okay. Right? The number of keys we have within a node is not going to be massively large. So yeah, it's linear scan, but it's not too bad because it's in memory. One optimization you can do if you have certain data types that are fixed size, you can use SIMD to do vectorized operations. Who here is taking 418? All right. What's that? You're taking it right now. Have you covered SIMD yet? Yeah. Right. SIMD basically means single instruction, multiple data. So think of like it's a single CPU instruction that allows you to do some operation on multiple data items at the same time. So SysD is what you normally think about, like one single instruction, single data, like 1 + 1 = 2. Like you take the register one for one, the register for the other one, you add them together, single instruction, and it produces one output. SIMD allows you to take a single instruction and take a vector of data and do some operation on it and produce a vector as output. So to do something like this, so say I have you can use a 128-bit SIMD instruction. This is Intel intrinsics or x86 intrinsics. So I can take the first 4 keys, 4, 5, and 6. I can then build a vector of just the key I'm looking for, 8. And then in a single instruction, I can do a comparison of the input vector with my target vector, and it'll produce a bitmap that says, here's all the tuples, or here's the offsets of the tuples that matched. In this case here, none of them matches, but it's a single instruction to do this comparison and produce the output. And there's other SIMD instructions that then do, find all the ones to see whether I have a match or not. In this case here, I don't have a match, so I just slide over, do the next SIMD instruction on this. In this case here, I only have 3 keys instead of 4. So I did, the last one's ignored. And now I find a match, I see a 1, I know I find the thing I'm looking for. So again, instead of having to do sequential 1 by 1, I can do a smaller number of instructions to do this in parallel. x86 has this, ARM has this, RISC-V has their own. Like a bunch of systems have vectorized instructions for this. But it only works if it doesn't work on strings. If things are variable length, you want fixed length values. Another obvious choice is to do binary search, because if everything's sorted, I just jump in the middle, look for key 8. I know key 8 is greater than 7, so I want to look at the next side, binary search over here, and eventually land in the middle, right? That's pretty obvious. And the last one is rare. So no commercial system or real system actually does this, to do interpolation, where we just do some math and say, well, I know I have a densely packed array of keys with no gaps, like 4, 5, 6, 7, 8, 9, 10. And the key I'm looking for is key 8. So I can just do the simple math and say, well, if key 8 is going to exist, then if I just take the min value, the max value, jump to my offset, then I know it's going to be here, right? It's not, if you land on something that's not 8, then you know it doesn't exist.
But like, what if the array is not packed?
If you can't, the question is, what if the array is sparse, not dense, it's not packed? You can't do this. That's what I'm saying. It's a huge win if you could do this, but you can only do it in rare cases. All right, 3 minutes left. Let me get through, I'll get through 4 of these. All right, again, it's a data structure from the 1970s. Look at all the crazy you can do with this and make these things actually work. And this is what real systems are actually doing. All right, first one is pointer swizzling. This one is super common. I don't know why it's called swizzling. I didn't make the name up. It's the 80s. I think it's a reference, but I wasn't there, so I don't know. All right, so when we do a lookup, so when we follow pointers in our B+ tree, what are we doing? Right? We're not actually storing memory pointers. We're storing page numbers. So if I want to traversal, find key greater than 3, the first thing I got to do is look at my key, my root node, find, it says 6. I know I want to go down to this side. Okay, well, how do I get down to that leaf node? Well, I'm going to have a page number in my root node. Tells me how to go down there. So to get that page, I got to go to my buffer pool and say, hey, go give me page 2. Give me back the pointer in memory for the frame that has that data. Okay, once I get that, then I can do the traversal. Now I got to scan along the leaf nodes following the sibling pointers. Same thing. I want to get page 3. What do I got to do? I got to go to the buffer manager and say, hey, go give me page 3, right? But because now we know it's a hierarchical data structure, we can have some guarantees about the order in which things would get evicted if we're a bit careful about this. So instead of actually storing the page numbers in the pages, we actually store just the pointers to the actual data. We got to pin those pages, make sure they don't get swapped out and replaced with something else, right? But now when I have a swizzle pointer, I basically have a little region in my page where I can store the actual raw memory pointers, and I have to know that if it gets evicted to the disk and bring it back in, those pointers are not valid anymore. But now I can just do my look at my page and say, here's directly to the location that I want as I do my traversal. And you get a huge win if you do this. And the data structure provides this nice guarantee where we would say, we can know that we can have it be, I don't want to evict anything in a root node, or sorry, in an inner node if one of its children node has been swizzled or is in memory. So this makes sure we have some guarantee about how we order things to make sure that we don't end up with pointers that go to nowhere or pointers that go to a frame that has no longer the data we want. All right, the last one I want to talk about is, well, I'll go two more. So it should be clear that modifying the B+ tree when we have to do splits and merges is expensive. If it's inserts, we just keep inserting to one side, and if our node has space for it, that's fast, that's fine. Same with deletes, right? But the worst case scenario is that we do a delete or an insert, and we got to reorganize the entire tree to make sure that it's balanced, right? So ideally, it'd be kind of nice if we can delay having to do these splits and merges to accumulate a bunch of them and then do them in a batch rather than having to treat them as single inserts and updates one at a time. So this is what's called a right optimized tree. I think Wikipedia calls them the fractal trees. That was sort of like the brand name, right? Like Kleenex is the brand name of face tissue, right? So fractal tree is the brand name. The generic name is also called a B epsilon tree. And the basic idea here is that in the same way you saw in MySQL for compressed pages, they added a mod log in front of the page. We're going to add a mod log in front of every single node. So now, anytime we want to do an operation, we don't have to maybe traverse all the way down to the bottom of the tree. We just find the first spot where we can put something in a mod log and put it in there. So I want to insert 7, right? So in a regular B+ tree, I'd have to traverse all the way down and then insert it on this node here. Instead, what I'm going to do is I'm going to put an insert entry in my mod log. It's like the mem table, more or less, or not the mem table, like how in the log structure storage, we were storing these log records, like here's the changes I made, without maybe actually applying them. So I'm going to put the insert 7 in my mod log. Now I'm going to do delete 10, same thing, and I put it in there, right? So now if anybody comes along and wants to do a lookup on 10, when you do the traversal, you normally do it in a B+ tree, but you check the mod log first. And if the mod log contains the thing you're actually looking for, the actual key that you want, then you can stop right there because you found what you want and you don't have to do traversal. So to find 10, I land in the first root node, I look in the mod log, I see delete 10. Well, I know that at that point, the last thing that happened to key 10 was it was deleted because it's at the top of the tree. So I can go ahead and stop my search because I know it's not there. Even though physically it's still in the leaf node here, and I got to be careful. Anybody scans along and tries to find it, right? There's actual bookkeeping I have to do. But in this case here, I don't have to propagate the changes immediately. So what happens is when the mod log does get full, like I want to insert 40, now I don't have any more space in my mod log, my root node. So then I got to propagate the changes down, right? And then whether you just go one level down or all the way down depends on the implementation. So this is kind of getting the benefit of the log structure merge tree, but in the context of a B tree. So you're kind of blending the best of both worlds. Okay? This is very rare. I think the data structure was invented in the 90s, but very few systems actually implement this. There was a system called Tokutech. They got bought by Bracona. The new professor, William Kuzmel, in computer science, his dad was one of the inventors of that data structure, even though he claimed not to be a database person. The best implementation probably that was out for a while is this thing called Splinter DB from VMware. That I think has been discontinued because the guy left to go to Cornell. But relational AIs and ChromoDB out of China. Relational AI is in the US, ChromoDB is in China. Those are the two systems that I know that are pushing this pretty hard. Okay? All right. Quick question. Yes, go for it. So why isn't this more popular? Because it's hard, right? Because you have to, like I said, if I scan along the leaf nodes, I got to know how to find up above. Okay? All right, guys. See you on Wednesday. Hit it.
Cash money, click, flips, acrobats over tracks. 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 Get the fortune, motherfucker fame. Maintain but never strain flow with the grain. Get the fortune, motherfucker fame. Maintain but never strain flow with the grain.